the electronics, so you know if something was manufactured in a factory that it was made in that factory. There's no counterfeit going around. So sometimes you can fingerprint it using color on top of black and white. And then going forward, everything I've shown you is two-dimensional, but there's no reason why this type of technology cannot be applied to 3D. Again, for portability. You can make very lightweight portable 3D systems that could do head scanning for like stroke patient detection. And there are other applications in here as well. So we've done tomosynthesis work with this type of detector, and for sure you can see the same type of benefit in 2D, you can see in 3D. In this particular case, the noise is a little high just because of the way we took the images with very low dose, but some algorithms can clean this type of stuff up. But the point of this is really, there's a lot of future for this type of technology. This is a nice example from that same study. We were able to separate materials during the tomosynthesis. In this case, we were able to separate calcium from uric acid. We designed this specifically for a kidney stone application. So because in kidney stones, 80% are calcium stones and 20% roughly are uric acid. There's a few other esoteric varieties, but those are the two big ones. So if you can see the stone and what that stone is in vivo at the hospital when you show up with a grade 10 pain in your kidney, it's better because the treatment can be started sooner, and you don't have to take your Tylenols and go home and deal with it until they finally do something to try and get the stone out of you. But this is a great way to do it in vivo. Okay, so we talked lots about spectral. Let's switch gears for a second and go to the other imaging that I was mentioning, and this is phase contrast. So what do I mean by phase contrast? Remember I said X-ray, if you think of it as an electromagnetic wave, it has multiple components to it. You've got your amplitude, you've got your phase, you've got a frequency. So phase is what we're going after in this case. And it just so turns out that if you look at amplitude, X-ray is good for materials that are very dense with high atomic number, like calcium or steel, because the amplitude variation is easy to detect. But if I took an X-ray and I ran it through glass or water, the amplitude doesn't change at all. So actually you cannot tell if you're going through glass or water with an X-ray because the amplitude stays roughly the same, especially if it's thin glass. If it's very thick glass and it's got like borosilicate, yeah, maybe you can see it. But like fiber optic or like very thin glass, you're not going to be able to see it. So this is where phase comes in. It just so turns out that even though the amplitude doesn't change, the phase changes considerably in glass, water, air, as long as there's a boundary with air and water, air and glass. So in situations where you have a very low Z, low Z type of material, the phase change can help you get an image where an attenuation would not be able to help you get an image. So that's why we use phase contrast, okay? And that's really what we're talking about here. And there are many ways to get this type of phase. You can use gratings, which is typically what you do in high school. We would play around with diffraction gratings to see what was going on. With us, we do it using two ways. You can use a grating, but an X-ray grating is not so easy to make. You can also use propagation. So if there's a phase change and you create some distance between the detector, the wave is allowed to propagate. That phase change can result in some nice interference patterns that you can pick up. The phase change is very small. It's like in microradians. It's tiny. But if you have enough distance, even a 1 microradian variation can result in a very large interference pattern. In fact, back in Australia, maybe 30 years ago at the synchrotron facility, they demonstrated this for the first time. They looked at the phase change and they showed when they put a detector about 10 meters away from the object using a very powerful X-ray source, they showed the phase change. Now, practically speaking, you can't put the detector 10 meters away, otherwise you need a synchrotron. So that's where we come along, and we created what I think still is the world's highest spatial resolution X-ray detector. It is a 8 micron direct conversion pixel with selenium, which I'm very pleased to hear that Ahmed is going to be bringing to this university. That material allows us to place the detector centimeters away from the source. And because we can place it centimeters away from the source, I can use a low power microfocus source, which are quite inexpensive. And now something that would ordinarily require a synchrotron can be done in your lab right here. Right? That's the transformation in technology. So it brings an X-ray microscope with tremendous power at the fingertips of scientists who would need that. So that's a brilliance detector. It's got a lot of interesting features in it. This was an image taken at a US synchrotron, because when they heard about it, they said, oh, we've got even more applications that we can do with something like this. So they got into something called dark field microscopy. They got into Bragg, coherent diffraction imaging. And I mean, they're even trying to, some of them trying to prove the existence of God with this type of technology. There's some God particles they're chasing after. I think they're called like neutrinos or something, beta decay neutrinos. Anyway, that being said, more at home for more pragmatic people, you can use it for all sorts of science, like biological science, life sciences, 3D printed, additive manufacturing, et cetera, et cetera. There's a lot of things you can use this for. There's some performance of the detector. It's one of the highest spatial resolution detectors in the world. As you can see, it's MTF. You can get roughly 10% MTF at 100 line pairs per millimeter. So that, of course, is the advantage of selenium. It gives you this exquisite resolution, and that's also the reason why you can create phase contrast images. This was one of the first systems we built in the university. I included this because it's nostalgic. And Ahmed remembers that we just talked about it in the morning. There's the blue source. It's a small microfocus source from Fisher, very low power, barely a couple of watts. But we were able to get phase contrast images in a lab with a home-built system, just using something like this. Just to give you an idea, like what do I mean by phase contrast images? This is a great comparison. What you see here is the seed of a bell pepper, capsicums. They're usually about 3 to 4 millimeters, quite small. And if you look at it, and I'll zoom in so that you can see it more clearly, this would be the image without phase contrast. This would be the image with phase contrast. And so you can kind of see, even with this projector screen, the level of detail is shocking. What you can see with the, and like I said, this is something that you wouldn't be able to do with a regular X-ray. It's quite challenging. So the company that commercialized this technology took that device and made a benchtop micro CT out of it so that it can be used by scientists. And so a lot of the images that you'll see were actually taken using this micro CT. And there's, another micro CT that's coming out that's a little bit larger. It's got some more features in it. But like I said, the use cases are quite numerous. Additive manufacturing, 3D printed, composite materials, food, phone lenses, cell phones, kidney stones, implants, plant seeds, histopath, specimen radiology, biopsies, semiconductors, PCBs. Like the applications are quite it's a platform for a lot of things. This is an interesting example. This is Kevlar. Kevlar, of course, is a very low Z composite material used quite a bit in, most people hear of it in bulletproof vests, but it's actually used in aerospace for designing aerospace panels. This is an X-ray image of Kevlar. It looks like an optical image. You wouldn't believe it, but this is actually 3D reconstructed based on the micro CT. You can see each of those fibers is in the 10 micron range. So quite something. This is electronics. You can kind of see how the bonding patterns are set up. Again, these are also electronics, specifically sockets used in some sensitive electronics. You can even see the spring inside the socket. These are all in like the 10 to 20 micron type range. Here's the metallization of a semiconductor IC. If you're in the semiconductor business, you want to look at your top metallization. This is a great way to do it. We use them for soldering. We use it for through silicon vias. If you're doing 3D ICs where you're putting memory on top of a regular semiconductor, you want to see if the copper via has proper fill or through glass vias. You can use this technology. Again, each of these vias is probably 20 to 30 microns, and you can see the fill quite easily, because if I zoom in, these vias are full. I had to take the shot at a 3-degree angle because otherwise it just looks like a dot. At least now I can see the side of the via. But you can see the vias on the right are not filled, and the vias on the left are filled. Great way to be able to do electronics. Here's a seed again, a bit more detail. This was a nice one. This was one of my other PhD students. He was in the biological application space. This is the image of the articular cartilage of a little mouse. Okay? So the leg is about this big, and the cartilage is about 50 microns. What's unusual about this is you cannot see cartilage with an X-ray. Anybody will tell you if you want to see cartilage, you're going to need ultrasound. But this is 50 micron resolution, so an ultrasound will not work. So the only thing that can resolve this is an MRI, where you would run it for like an hour or two to resolve it down to 50 microns. We did this in a single exposure, like literally 200 milliseconds, right? So nice application, lot of potential here. This is an implant, a titanium implant. We've got people who grow bone for a variety of reasons. Again, you can see the trabecular bone structure quite clearly. Food, chocolates, if you want to quantify, this is a problem in our food industry. They constantly keep processing the food, and now because of the inflation, they keep trying to fool the consumer. So you're still getting the same size of chocolate, but they've hollowed it out inside. So you're not getting as much chocolate. The weights of the chocolate has gone down. So this is a way to quantify how many pores you have inside the chocolate. Yes, a pet peeve. Pharmaceuticals. If you want to do quality control on the coatings in the pharmaceuticals, you can do that. This is a CT of that same pharmaceutical. This is a very commonly used pharmaceutical for indigestion. It's Losec, isopramazole, used as an proton pump inhibitor. It's a PPI. And so the way they do time-released capsules is inside each of these capsules, they put in these little particles, and the particles have a coating. Actually, they have multiple coatings on them. So this can be used to resolve that coating to see how good it is, and if you want to have a certain distribution of coating. Kidney stones, if you want to look at the structure of the kidney stone, beautiful views. This is a multi-material kidney stone, you know, lots of different things as it forms and waves. It's you can really see quite a lot of beauty in this. It has a lot of similarity to how rocks form in the water, underwater in oceans and coral. But this happens inside a body. It's like the waves of liquid washing up in the kidney, and then it forms these stones over time, and different materials crystallize and grow. Remarkable, actually. So, you know, I showed you phase contrast, and you can see more, but I teased you with a line right at the beginning. I said, we can do quantitative imaging. And so you would have asked, well, what is quantitative about phase contrast? Like the phase helps you see the low density material. So I've got better visualization, but what's the quantitative element? So this is where the quantitative element comes in. You can do quantitative with the method I showed you, but it's kind of tricky because you're solving for two variables with one equation. It's very hard to do. You have to make assumptions and you can be wrong. In order to solve for two variables, you need a second set of information. So the way you do that is you introduce a grading. So we put in a single grading. A grading is nothing more than exactly what it sounds like. A piece of semiconductor with different heights and X-ray attenuation. So some X-rays pass through some parts unimpeded, and in other parts they get absorbed. So we built these very high resolution gratings, and we said, now that we've got the quantitative element and we can solve this equation, it's called the transport of intensity equation, we can extract phase information in addition to scatter information, along with the attenuation. Okay, so to test this out, we said, let's see if we can separate powders. So in this case, I was in the kidney stone space. I took a particular interest in kidney stones, so we got a whole bunch of different powders. Calcium oxalate, phosphate, these are different types of kidney stones. Struvite is a magnesium-containing kidney stone. That's actually the most dangerous kidney stone. Apparently, in the old days, people would die because of that kidney stone. Literally, all the kidney stone deaths happened because of the stone. It's very prone to infection. And then, of course, uric acid and cysteine. Cysteine is a genetic type of kidney stone. But, you know, what I want to show you is this graph. It's a very interesting graph. On the x-axis is transmission. Transmission is the analog of attenuation, like a intensity, okay? On the y-axis is scatter, how much that material is scattering. In this particular graph, what you see is that blue and green are calcium-containing stones. They tend to attenuate or transmit not so much signal, which is expected. Calcium is a high Z atomic number material. But on the right-hand side is cysteine, uric acid, which tends to pass X-rays. So with a regular X-ray, I can separate by attenuation uric acid from calcium. What I cannot get is magnesium, because magnesium has the same attenuation as uric acid. So if you use a conventional CT to diagnose the type of kidney stone, you would miss magnesium. You might think it's uric acid because uric acid happens to be much more common. You have to do spectroscopy if you want to find this. But with X-ray, for the first time, the scattering information, magnesium powder scatters differently from uric acid. It allows you to differentiate between magnesium and uric acid, right? So this is another advantage, a quantitative element, if you will. And I mean, I did this with kidney stone powders, but you could do it with any kind of powder. One of the obvious ones would be like narcotics, if you wanted to, or pharmaceuticals, if you wanted to be able to tell the difference, right? You can use this type of technology. And then last but not least, you can do CT with this as well. It doesn't have to be 2D. These are very fast scans of CT. The top is a transmission scan and the bottom is the scatter scan. You can see how the scatter image looks quite different from a transmission image. And that's where the quantitative information starts to pop up. Okay. I think I've used up my 45 minutes, so I'll stop. Happy to take questions.